In modern naval warfare, fire is a force of destruction that has taken a greater toll of men and ships than any single form of enemy action. The impact of a hit, with its accompanying explosive flash, invariably starts one or several fires that may prove more destructive than the direct action of the bomb or projectile. Even a near miss will often set up a series of small fires that, unchecked, may result in disaster. For in spite of the all-metal construction of modern ships, fire, once it has gained headway, will spread from compartment to compartment, igniting supplies and stores, fuel tanks and living spaces, personal effects, and much of the gear necessary to ship maintenance and fighting efficiency. Therefore, a thorough understanding of the nature of fire, its control and extinguishment is of vital importance to all shipboard personnel. From casual observation of a simple wood fire, it seems that the wood itself is burning. Actually, only the vapors given off by the logs supply the fuel that feeds the flames. This action can be readily seen in a simple laboratory experiment. A small quantity of wood shavings placed in a flask are heated by a Bunsen burner. The vapors rising from the heated wood can be ignited at the mouth of the flask. This is true of nearly all combustible materials, whether in a liquid or solid state. Here, soft coal is burned in the same manner. Even paper, which is not ordinarily regarded as vapor-producing, when heated, gives off vapors which can be burned at some distance from the paper itself. Most solids must first be converted into a liquid state before vaporization takes place. With paraffin, the melting stage is apparent. The entire process of fuel vaporization is visible in the burning of a candle. The ignited wick melts the paraffin into a liquid. The liquid flows into the wick and gives off vapors that feed the flame. Observe how the vapors rising with the column of smoke can be reignited. This action can be shown effectively in slow motion. When the candle is snuffed out, vapors are still being given off in sufficient quantity to be ignited at some distance from the wick. Many liquid fuels, usually regarded as highly inflammable, must also be heated before burning can take place. Fuel oil, for instance, cannot be ignited without preheating. The temperature at which an oil begins to give off vapors that can be ignited is known as the flash point. The flash point of number 6 fuel oil is 150 degrees. At a slightly higher temperature, it gives off vapors in sufficient quantity to sustain combustion. This is known as the fire point of the oil. But since there is usually but 4 or 5 degrees difference between the flash point and the fire point, for purposes of simplification, we shall refer to both as the flash point. Other oils have even higher flash points, varying according to their physical properties. Most lubricating oils must be heated to over 400 degrees before they will burn. On the other hand, more highly volatile liquid fuels, such as gasoline, alcohol, naphtha, or ether, have flash points so low they can be ignited readily at room temperature. The fire hazards that these liquids present are due to the fact that even at low temperatures, they are constantly giving off highly inflammable vapors. The flash point of gasoline is minus 45 degrees, 77 degrees below freezing. And while the ever-present vapors are not visible to the naked eye, they may be observed by means of a shadowgraph, a shadow image produced by means of a powerful arc light that reveals the vapors. The vapors, being lighter than the liquid, yet heavier than air, can be easily distinguished from the gasoline. The rate of vaporization is indicated by the manner in which the vapors overflow the beaker, which is only partially filled with the liquid gasoline. In this shadowgraph, an empty gasoline container is used. Only the vapors left in the container are being poured into the beaker. The flash point or fire point of a fuel, however, should not be confused with the temperature necessary to ignite the vapors. For unless a source of heat, considerably hotter than the flash point of the fuel, comes into direct contact with the vapors, the fuel will merely continue to give off vapors without burning. The second essential factor in the process of combustion is oxygen. Without oxygen, even the most highly inflammable vapors will not burn. Under normal conditions, a flame draws the amount of oxygen necessary to sustain combustion from the air. But when burning in an enclosed space, as in this glass bell, the supply of oxygen is gradually consumed. The flame diminishes. When the oxygen content falls below 15%, the flame becomes suffocated and dies out. The part that oxygen plays in supporting combustion can be further illustrated by this experiment with steel wool. A flask is filled with pure oxygen. A wad of steel wool is then held over a flame. It produces only a slight glow. But when the glowing steel wool is placed in the oxygen, it burns intensely. This same principle is employed in a cutting torch. When only the acetylene gas is used, there is no effect on the metal. But when oxygen is added under pressure, a flame is produced so intense and containing so much oxygen that it will burn through the metal. Under normal conditions, the oxygen in the air combines with vapor in correct proportions to sustain combustion. With a regulated flow of vapor in an open space, the ready mixture of the two elements is evident. The greater the flow of vapor, the greater the mixture with oxygen and the larger the flame. This action is caused by the heat of the flame. The hot air currents rising from the flame create a draft suction that draws a steady flow of oxygen into the flame area. But with the flow of oxygen restricted, as in this partly filled tank, combustion is incomplete. Here, the unburned vapors rise high above the tank, where they mix with a fresh supply of oxygen, then burst into flame. Gasoline vapors can be ignited only where they mix with oxygen. To the surface of this beaker of gasoline, the vapors will not ignite. They are too dense. The mixture is too rich. Here, the mixture is too lean. In this vicinity, the mixture is within the explosive range. But the explosive mixture may occur anywhere in the vicinity of gasoline stores. As the shadowgraph reveals, gasoline evaporates so rapidly, even at low temperatures, that the vapors overflow the container. Being heavier than air, they flow downward or drift for considerable distances on currents of air. These characteristics account for the hazardous nature of gasoline. Here, a cloth is immersed in gasoline and placed at the top of a trough. The vapors seeping from the cloth act as a fuse, carrying the flame back to the cloth. The same experiment in shadowgraph reveals the action of the vapors as they flow down the trough to the candle. That combustion cannot occur without a proper mixture of vapor and oxygen can be illustrated with this simulated gasoline tank. An electric spark is set off inside the tank. Because of the covering which limits the supply of oxygen, the mixture is too rich to ignite. However, when the gasoline is drained off, it is replaced by air. The vapors are diffused with a greater amount of oxygen. With the tank empty of liquid and the vapors diffused with a sufficient amount of oxygen, an explosive mixture is established. We can now observe how an explosion may occur in an empty gasoline tank. As the cover is burned away, additional oxygen is drawn into the tank. It combines with the heavy vapors at the bottom, and the mixture burns rapidly. Up to now, we have discussed the vaporization of fuels. We have seen that most fuels must be heated to their flash point before they will burn, while the more volatile fuels have a flash point so low that they vaporize rapidly at room temperature. We have also seen proof that vapors must be mixed with oxygen before they will burn. There is but one other factor: the temperature necessary to ignite the mixture. With fuel at its flash point and the vapors combining readily with air, the mixture may be regarded as in a state of readiness. Combustion, however, cannot occur until further heat is applied. In this case, the heat of the flame provides the added temperature necessary to ignite the mixture. Here, a high voltage electric spark is used. But both flame and spark provide temperatures much higher than necessary for the fuels used. Gasoline vapors, for instance, can be ignited by the glow of this tiny electric coil. But a heated soldering iron that fails to ignite gasoline is hot enough to ignite paper. While phosphorus, when exposed to the air, will burst into flame at room temperature. The ignition temperatures of many fuels have long been established. The range of heat required can be demonstrated with this apparatus. The two fuels at the left of the screen require no preheating, their flash points being gasoline 45 degrees below zero and alcohol 55 degrees above zero. The fuels at the right are heated to their flash points. Fuel oil 150 degrees, linseed oil 450 degrees. The coils suspended over the beakers are all controlled by a single rheostat. When the heat of the coils reaches the ignition temperatures required for each of the fuels, combustion results. Gasoline at 495 degrees. Linseed oil, 650 degrees. Alcohol, 700 degrees. And fuel oil at 750 degrees. Note the wide temperature differences between the flash points and the ignition temperatures of the different fuels. Heat from any source will raise the temperature of an inflammable mixture to its ignition temperature if the required degree of heat is present. Here, a heated metal plate ignites a beaker of gasoline as soon as the temperature of the metal reaches 495 degrees. Since the heat of a flame is greater than the ignition temperatures of nearly all fuels, a fire, once it has gained headway, will spread rapidly. The unheated fuel oil in this pan cannot be ignited with a small flame. But primed with gasoline, the heat of the burning gasoline vapors raises the temperature of the surrounding oil to its flash point. The oil vapors in turn ignite, and the fire spreads over the entire surface of the oil. The rate of burning is governed by the surface area. Only the fuel coming into contact with the oxygen in the air is consumed. Gasoline in a small beaker will be consumed slowly, but the same amount of gasoline spread over a large area will burn rapidly and intensely. Because the greater the surface area, the more readily oxygen reaches the vapors. The surface area of a material in proportion to its volume also affects the readiness with which it will ignite. For example, here are two identical blocks of wood. Both have been cut from the same piece of timber. One of the blocks is reduced to a pile of shavings, greatly increasing the surface area of the material. The solid block merely chars and absorbs the heat of the small flame. But the same flame readily ignites the shavings. Since the starting of a fire involves three elements, fuel, oxygen, and ignition temperature, these elements may be likened to the three legs of a triangle. For fire cannot occur unless all three are brought together. Let us examine a few common causes of shipboard fires in terms of the fire triangle. A cigarette is carelessly discarded. It comes to rest on some scraps of paper. As we have seen, paper has a very low ignition temperature. The heat of the glowing cigarette is sufficient to cause the fuel, in this case the paper, to give off vapors. Oxygen is present, and when the vapors are given off in sufficient quantity, they flash, the heat of the cigarette being high enough to supply the ignition temperature. Because of the surface area, the fire spreads rapidly. As it spreads, the fire grows in intensity, building up higher temperatures, causing more and more vapors to be given off. The heat of the flames causes the hot air to rise, drawing in additional oxygen to combine with the vapors and feed the flames. Gasoline fires or explosions are often caused by static electricity, particularly during loading or fueling operations. The electric charge is generated by the friction of the flowing liquid. When the nozzle is grounded by contact with the tank, the electric charge drains off to ground. But when the nozzle is not in contact and no bond or ground exists, a static charge is likely to build up. If permitted to accumulate, the static electricity gains in voltage and seeks an outlet. Since the mouth of the tank is the nearest metal conductor, a spark hot enough to ignite the vapor-oxygen mixture will span the gap between nozzle and tank. The origin of many bilge fires has been traced to oily rags and other materials discarded or inadvertently dropped into inaccessible places. Here, an oily rag has fallen on a steam line. The temperature of the pipe starts the process of vaporization. The heated vapors entrapped in the rag accumulate and build up a higher temperature. In time, the ignition temperature of the oily rag is reached and a fire is started. The time required for this process of combustion depends upon the temperature of the pipe and the physical properties of the oil. In contact with oil in the bilge, the flaming cloth heats the surrounding oil to its flash point. The oil vapors mix with the oxygen in the air, make immediate contact with the flame, and a bilge fire is started. Because of the large surface area of the oil, the spread of the fire is unrestricted. While these examples may appear commonplace and avoidable, many unavoidable and unforeseen conditions are often brought about as a result of enemy action. A direct hit is usually accompanied by an explosive flash so hot that it will sear or ignite all the combustible materials in the damaged area. A near miss will often rupture fuel tanks, causing oil seepage and flooding of decks. Shrapnel has been known to puncture gasoline trunks and pipes, liberating gasoline vapors that travel considerable distances through passageways and ventilation ducts. vapors, even at a 1.5% mixture with air, can be ignited by a short circuit or the tiny spark of an electric motor. Once started, the fire can easily spread throughout the vessel. An intense fire in one compartment transmits heat through the metal bulkheads to adjoining compartments. As the temperature of the bulkhead is raised, materials on the other side of the bulkhead become heated. They give off vapor that mix with oxygen. The inflammable mixture comes into contact with the heated bulkhead and ignites. Even passageways and compartments barren of stores or other combustible materials can transmit heat and fire from one region to another. Paint, largely because of its oil and resin content, is highly inflammable. Heat transmitted through metal bulkheads will cause the paint to blister and scorch. When the ignition temperature of the paint is reached, it will flash and burn across the entire bulkhead. Since fuel requires both oxygen and ignition temperature in order to burn, the extinguishment of fire can be accomplished in two ways. One, by restricting or cutting off the supply of oxygen, or two, by reducing the temperature below the ignition point. The principle of extinguishment, usually referred to as smothering off the oxygen supply. Extinguishment with the use of carbon dioxide is based upon the smothering principle. Portable carbon dioxide apparatus provides a quick and convenient method of excluding oxygen from a burning area. The action of carbon dioxide on a fire can be shown more clearly by filling an open container with the inert gas and pouring it over a flame. Being heavier than air, the carbon dioxide smothers the fire by displacing the oxygen at the base of the flame, leaving a blanket that prevents air from mixing with the fuel vapors. The value of this type of portable extinguisher is the speed and ease of operation it provides. It is most useful in confined spaces for extinguishing incipient fires or holding them in check until additional equipment arrives. Carbon dioxide is particularly valuable in extinguishing fires in electrical equipment and machinery. For the inert gas is a non-conductor of electricity, and since it leaves no residue, will not damage critical equipment. Large oil and gasoline fires can also be extinguished by the smothering principle. But with large fires involving liquids, foam should be used as the smothering agent. Here, foam is being applied to a tank of burning fuel oil. Notice that the foam is not being poured into the oil. The stream is directed at the opposite wall of the tank and caused to flow gently over the surface of the oil, providing a thick blanket of foam that prevents the oil vapors from mixing with oxygen. Extinguishment of the fire is not complete until the entire surface of the oil is heavily blanketed. Any disturbance or breaking up of the foam blanket will cause a reflash. For until the area has been cooled, heated vapors that escape through crevices or gaps in the foam blanket are free to mix with oxygen and reignite. This small-scale laboratory demonstration clearly shows the smothering effect of foam. Foam as an extinguishing agent is particularly valuable in fighting hot, inaccessible oil fires, such as may occur in fire rooms and bilges. For a stream of foam can always be applied through a hatch or a small opening cut through the deck. Stream, however, must be directed against an unobstructed bulkhead or other place from which it will flow gently to the burning surface. Due to its light weight and consistency, foam flows easily on the surface of the liquid and surrounds any obstruction in its path. But the speed of application is important, for while foam possesses an insulating quality, when subjected to heat for a considerable period of time, it tends to harden, crack, and fry off, releasing vapors which will reignite. Whenever foam is used, it should be applied quickly and in sufficient quantity to provide a thick, solid blanket over the entire surface of the liquid. Only then will extinguishment be complete and reignition prevented. Steam smothering systems are installed in the machinery spaces of most steam-propelled vessels. They, too, operate on the principle of extinguishing fire by displacing oxygen. When steam is admitted into a confined space under pressure, the inert blanket provided by the steam displaces the oxygen at the surface of the burning oil, smothering the fire. Steam smothering, however, must be used in a confined space, and its effectiveness is limited to oil and liquid fires. When used on materials other than liquids, steam will extinguish the flames surrounding the exposed surface of the materials. But sufficient oxygen will remain entrapped in the mass to sustain combustion. The deep-seated portions of the fire will continue to smolder and burn. When the steam is dissipated and additional oxygen is drawn into the space, active combustion will reoccur. The second method of extinguishment is the reduction of temperature below the ignition point. Water has long been used for this purpose, but its effect upon fire is not generally understood. A solid stream of water will not extinguish an oil fire. Yet the same amount of water, in the form of a fine spray or mist, will extinguish it quickly. The principle involved is, mainly, the rate at which the surface is cooled. A solid stream of water directed at a hot plate produces only a small amount of steam, indicating that only a small area is being cooled. But the same amount of water, finely diffused, produces a considerable amount of steam, indicating that a large area is being cooled by the water. This principle of temperature reduction is used today to control and extinguish all types of fires. This tank of burning fuel oil, for instance, is brought under control quickly and easily with the use of water in the form of fog. When the finely divided particles of water reduce the heated area below the ignition temperature of the oil, the fire is immediately extinguished. Fog also produces a smothering effect that aids extinguishment. As the tiny particles of water reach the flame, a steam blanket is produced that smothers the unburned vapors, preventing them from mixing with oxygen. Before extinguishment is complete, however, the entire area must be cooled below the ignition temperature of the oil to prevent the vapors from reflashing. The heat-absorbing qualities of fog also afford the fire party adequate protection in entering a burning compartment or passageway. For when the spread of the water particles spans the width of the burning area, it acts as an effective water curtain. The use of fog even makes it possible to attack fires from the lee side. Here, with the use of two fog nozzles, the fire party moves through the flame area to extinguish the fire at its source. Reducing the temperature below the ignition point of the fuel is an effective method of combating all types of fires. But to produce fog effective enough to combat fires involving gasoline or the more volatile light oils, approximately 100 pounds pressure is required. While the cooling principle can be employed in extinguishing all fires, some fuels burn more persistently than others. Materials such as bedding, cork, wood, hemp, and nearly all types of stores must be soaked thoroughly for complete extinguishment. Fires involving these materials may be attacked with fog to protect the fire party. The fog will also cool the general area of the fire by knocking down the flames. But a solid stream of water should then be employed to penetrate the burning material. Besides having a low ignition point, a mass of fibrous materials will retain sufficient oxygen to sustain combustion beneath the surface of the burning mass. Unless thoroughly saturated, the deep-seated portions will continue to smolder and burn. The heat will accumulate, build up additional vapors, and reflash. Immersion in water of all smoldering and charred portions is the only thorough method of reducing the temperature of these materials below their ignition point. The principle of using a cooling agent to reduce temperatures below the ignition point of the material also applies to powder and ammunition. In an open space, this grain of smokeless powder burns very much like any other fuel. There is but one important difference. Powder contains its own oxygen. Therefore, it burns more rapidly than other fuels. So rapidly, in fact, that when confined, it explodes. The effect of a cooling agent on powder may be illustrated with the grain of powder on the left. It is packed in dry ice, and while it can be ignited at the top, the cooling effect of the dry ice is evident. The flame burns feebly, then dies out. When ready ammunition is in the vicinity of a fire, it can be kept from detonating by cooling with fog. When magazines are threatened, they should be immediately sprinkled and flooded. While all shipboard fires resulting from enemy action cannot be prevented, they can be controlled and extinguished. To this end, a thorough knowledge of the nature of fire is of vital importance to all shipboard personnel. For with that knowledge, shipboard fires can be isolated, controlled, and extinguished. A fire in one compartment can be confined to that compartment by cooling bulkheads and decks of adjoining compartments, by removing fuels before they vaporize, and keeping bulkheads and decks below the ignition temperatures of the fuels, by diligently inspecting all compartments in the fire area for the presence of abnormal heat. Fire cannot occur unless all three elements of the fire triangle are brought together. Fuel in the form of vapor, oxygen, and ignition temperature. Therefore, the control and extinguishment of fire can be accomplished in two ways. One, by cutting off the supply of oxygen through the use of foam or carbon dioxide. Or two, by reducing the temperature of materials below their ignition point through the use of water. It should be remembered, however, that carbon dioxide should be used whenever possible on electrical and machinery fires, and that it is most effective in a confined space on small fires involving gasoline, oil, and other inflammable liquids. On all large fires involving inflammable liquids, foam should be employed, and the foam should be used in sufficient quantities to supply quickly a thick, solid blanket over the entire surface to prevent reignition. In extinguishing fires by cooling, water in the form of fog should always be used on gasoline, oil, and other inflammable liquids. Fog should also be used for cooling bulkheads, decks, and ammunition to prevent ignition, and for knocking down the heat and surface flames of fires involving non-liquid substances. But to penetrate the surface of these materials, a solid stream should always be used to ensure thorough and complete extinguishment. While it is often said that no two fires are alike, the principles of extinguishment shown in this film can be applied successfully to all fires. For it is upon these principles that all firefighting techniques are based.